So as I said, I actually got my PhD here and born and raised in LA, so it's nice to be here. Thanks to the organizers, I really appreciate it. I should also mention that I am one of the organizers of the Bay Area R User Group. And so if any of you happen to be in the Bay Area sometime, we'd love to have you give a talk. We're always looking for speakers. So, you know, if you happen to be around, let me know and see what we can do. Finally, Amy mentioned the slides are going to be on the web. Also on my website, I have to put it up, which I'll do as soon as the talk's done. But it is kind of hard to follow. Excuse me. It's kind of hard to follow this stuff sometimes. You know, so it'd be nice so that you could go through these things leisurely. So here we go. I'm going to introduce two R packages that my group wrote. The first one actually is being processed for CRAN right now. It's on my GitHub site. You'll get an address later. I'm not going to really focus on like the syntax of the calls and stuff like that. I'm going to talk more about, excuse me, why we wrote these packages. And it may become kind of controversial. It's interesting that, as I wrote here, they're both machine learning alternatives. And that's kind of a polite way of saying that I'm kind of going to be a little critical of machine learning. And so when we first came out with polyreg, the first one, it was interesting. I wrote about it on my statistics blog, and then somebody saw it there, and they put it on Twitter, and then people saw it there and put it on Reddit and wherever else, Hacker News. And there was an immediate controversy. The machine learning people, there must be some here, are very touchy, very defensive. And so some of them were very, very critical. They didn't even like the fonts in our paper. On the other hand, other people really liked it and said, you know, it's interesting that the director of the center here just said that Bruins should be game changers. One of the people who commented at that time said this could be a game changer. So that was kind of nice to see. So let's see what I'm talking about here. So I'm going to talk about neural networks and also something called TSNE, which is a machine learning visualization tool. And we have alternatives to both. As I said, you know, in the press we hear about machine learning all the time. When they say AI, they really mean machine learning. When they say machine learning, they really mean neural networks. Things have kind of devolved a lot, which is really unfortunate, I think. But you know, the neural networks people really, they do know how to get into the press. And you know, that's one of the reasons why we're doing this stuff, which is a little bit counter, let's say. You'll see what I'm talking about in a minute. Machine learning. That already sounds like science fiction. Neural networks really sounds like science fiction. And so, you know, the press loves that kind of thing, right? Plus, they reinvent all the terms. So they, you know, machine learning people don't like statistics. They don't like statisticians, I think. And so they reinvent everything. This is just a partial list. But if you are a speaker of statistics ease and you would like to know how to understand machine learning ease, I've got a partial translation tool for you here. You can look at it later. What is really happening with neural networks? Even the neural networks people would say that, you know what, we don't know what's going on inside, and that makes us a little nervous. And it really should, of course. And so there's even a paper that came out a few years ago titled Opening the Black Box of Neural Networks. In fact, I would have used that title for my talk. It was already taken, so I just said lifting the curtain. It was the same idea, right? What are they really doing? And not only that, once you find out what they're doing, the next logical step is to not do it. Okay? I hope you'll agree with me. You may not. We're going to present an alternative based on seeing what's going on inside that is simpler, easier to use, and much less fuss, fewer problems, and so on, and does as well or better. Also, a spin-off of all this with visualization. So I know a lot of you know what a neural network is. Some of you do not. There's going to be a brief 2 slides here introduction. Obviously, not enough, but just to go through it quickly. So you have your inputs, predictor variables. You have the output, which is prediction. It could be regression or it could be classification. More commonly classification. You have at least one hidden layer in between that does all the black box work. Each hidden layer consists of a bunch of units. It's interesting because they were originally called neurons, and then a lot of people start saying, you know, the brain doesn't really work that way. So now it's more common to call them units. You'll see a picture. And the inputs to layer I, so it's recursive. The inputs in the original predictors, we find linear combinations of them. They're input into the first hidden layer, and then there are linear combinations of those, and they go into second hidden layer, and eventually they get out to the last layer, and that's the output. Now, if you've never heard of neural networks before and you listen to what I just said, you would say, wait a minute, linear combinations in the first layer, then more linear combinations in the second layer. Wait a minute, linear combinations of linear combinations are linear combinations. So why have many layers? And so they have what are called activation functions to introduce nonlinearities, whatever that means. I've heard it actually called speed bumps, the activation function. So they'll go through something like a logistic function, not to be confused with logistic regression, but just as a function, the S-shaped curve, and to introduce this nonlinearity. So here's a picture. A lot of you know UC Irvine has a lot of data sets that you can play with, and there's one on diagnosis of vertebrae and abnormalities. There are 3 classes here, which come out the right-hand side of the picture. NO means normal, and then the other 2 are medical terms. The inputs are also medical terms, so it's just easier to call them V1 through V6. And all of these lines here are linear combinations with the numbers there being called weights. They're the coefficients in the linear combinations. The middle set of 3 circles here is there's only one hidden layer in this picture. The outputs out to the right-hand side go through the activation function, and then the outputs of that, or linear combinations, go into the next layer. And in case you've never seen this before, again, you can look at this at your leisure later. Here's a close-up picture of one of the neurons and linear combinations coming in. Output is then fed through activation function, and then fed in turn into the next layer in several different copies, each going through activation function. Here's the history, and I think the history is important. Neural networks are only new in terms of the LA Times, right? They've been around since the 90s. Nobody really paid much attention. Here's a little known fact for you. I should have put this in the slide. One of the real pioneers of neural networks was Kurt Hornick, who's a big R guy. And so, you know, when I tell that to people who know Kurt, and they're surprised. But actually, he had one of the seminal papers back like in the 90s or even in the 80s. But, you know, people didn't pay much attention. Then what happened in early 2000s, there were these competitions to do image recognition. And somebody won using neural networks. So after that, everybody said, oh, yeah, we should use neural networks. What happened was, and this is one thing I want to really clarify here. It's going to be in the next slide, but the success of neural networks with images is not really due to neural networks, I would argue. And I'm going to come to that next slide. But in any case, that's where it all really got, where it exploded. Okay? So we have a paper here, maybe with poor fonts, I don't know. We're going to have to, we are actually about to revise it on archive. We present an argument there that neural networks inside, that the black box, if you do open it, it's really plain old-fashioned polynomial regression. And I'll explain why in a minute. And I'm going to use an acronym here, NN equals PR, and neural networks equals polynomial regression. It's a slight oversimplification, but not much. Okay? And so that's our argument. That's what's really going on, and I'll explain why in a minute. And then we use this to speculate and talk about multicollinearity in neural networks. I'll come back to that if I have time, hopefully. And here's the key point, the third bullet. If what you're doing is really polynomial regression, why not do polynomial regression in the first place instead of this fancy neural network stuff? It's a lot simpler. Those of you who have used neural networks know that it's really a pain. You can have all kinds of problems. It's iterative. The convergence problems can be horrendous. There's something, I don't know if you've heard this term before, it's a great metaphor, the broken clock problem, meaning that the output comes out constant. It's like the clock that's broken never changes. And obviously that's not what you want as a constant prediction. So you can have local minima. You know, they're minimizing a sum of squares just like the usual linear regression, but it's a very complicated sum of squares, and what can happen is that you settle on a local minimum, which is not what you want. With polynomial regression, you don't have those problems. There's a unique answer. There's an explicit closed form solution. There are issues. Avoid the hyperparameters. The neural networks people have come up with all these tricks to try to get things to converge and converge to the right place. And so if you use Kara's formula, one of the authors of our paper here is the author of Kara's formula. I might as well just mention that now. So neural networks today, people like to feed it through something called TensorFlow. That's the next layer. Then the next layer after that, there's a popular higher level layer called Keras. And then there's a Keras R package. But it's not really, if you're an R user, it's not really very intuitive. So there's yet another layer called, another package called Kara's formula. And you can use that just like LM. And so one of my collaborators here, Pete Mohenti, is the author of that. And so the point is, if you use Kara's formula or any of the others, you have all these hyperparameters to choose. Granted, there are default values, yes. But if it doesn't converge, you've got to use non-default values. And how are you going to do that? And you can get into grid search and whatever. It's just really a pain. So if you use polynomial regression, you don't have that problem. Here's the key. We've never known it to fail. I'm going to show you some examples later. Every single data set that we've tried, our method has done as well or better than neural networks. Now, why? That's a funny question, right? Why? Right? Why should it be better? Because I just said neural networks are equivalent to polynomial regression, so why should polynomial regression be better? And the answer is that neural networks are sometimes settling on the non-global minimum. Okay, so it works. I mean, it's not just something we're talking about. And we do have this R package, polyreg, which I'll talk about a little bit in a minute. Here's some notation. So n, usual n cases, p-predictors, polynomials of degree d, PR, polynomial regression. It is in our package. It's motivated by what I said. It generates all possible polynomials in degree D.
Sorry, the mic is not working.
Okay, maybe I should stand closer. Or this one's supposed to work. You know, if I know it's not working, I can talk loud enough for all of you to hear me. I have 2 mics. Are they canceling each other out? It's like noise canceling headphones? Yeah, well, that's the problem. All right, let me know if it happens again. Now, just trust my powers of concentration. I know exactly where I left off. I was about to say the third bullet. You might think this is trivial. Oh, we're just generating polynomials. Why do we need a package for that? It's not so trivial at all. Because among other things, you've got to deal with the categorical variables. Now, you know, if you're using factors in R, and so you use factors the way they are, R internally is going to change them to dummy variables. And dummy variables, they're ones and zeros. You don't want to take the third power of ones and zeros. They're just ones and zeros. And so since the matrix gets quite large, you have to make sure you don't generate those. And then we have a predict function also, of course. And then you have to make sure the predict function follows the same polynomial that was generated in the training set. So actually, it's not easy at all. Anyway, we did it. We do get, if you think about it, all third-degree polynomials and 50 variables. That's a whole lot. And so there's issues of dimension reduction. We've got stuff for that as well. Here's where it is for now. Should be on GitHub soon. I mean, on CRAN soon. They keep putting more and more obstacles. You know how that goes. Okay. So, you know, I'm not going to go into the syntax and whatever very much. Here's the main function, polyfit. Of course, we've got a lot of options also. You can do PCA for dimension reduction. You have 2 choices of PCA for that matter. You can use LM or GLM. You can use, I noticed somebody's giving a workshop here today on multivariate LM, where the Y is multivariate. That was a really good idea to do that. Not a lot of people know you can do that, and we offer that as well. It actually turns out to do that. Doing that is actually better than using GLM for the classification case, because GLM is just too slow. You know, remember, we're doing prediction. So we don't have to worry about the niceties of whether, you know, whether a linear model is a good idea for binary data. It just works. You know, we're doing prediction. Anything goes. Okay? And then we do have a predict function and so on. So so here's my claim. Why is neural networks really the same as polynomial regression? So let's take a toy activation function here, the squaring function. Yes, I know nobody would ever use that in the neural networks world, but just as an example, here's the problem. Remember the picture. The original data, linear combinations of the original data go into the first hidden layer. They come out through the activation function. That means all those linear combinations are being squared if you use this function. And then you get to the next layer, they're being squared again. So now you're getting 4th powers and then 8th powers. So you really are getting 8th degree polynomials if you use this function, a toy function. I'm going to say a little bit more about that, but the last bullet here, as I said, your first layer you're getting 2nd degree polynomials, next layer you're getting 4th degree, then 8th, and so on. And so the degree of the fitted polynomial is growing. And actually, that's not a good thing. I'm going to come back to that. Wait a minute. All right, so, okay. So a neural networks person here, I guess there are some, but they're too polite to shout out. But they would say, no, nobody uses the squaring function as the activation function. Sure. But they do use things like sigmoid, which is logistic. And the point is, if you're doing anything like e to the x or anything like that, R, everybody here knows, I think, R is written in C. C uses the C library for something like e to the x. And they typically that's implemented using a Taylor series and finite one. And so you're back to a polynomial again, folks. Okay. Some of you know about ReLU, R-E-L-U. That, excuse me, that is not differentiable, but it is piecewise polynomial. So if you like, take everything I said about polynomials and replace it by piecewise polynomials. This is the same thing. Okay. All right. So, bottom line, literally, this last line of the slide, neural networks is really polynomial regression. And they're doing minimizing sum of squares. What are the implications? Well, first of all, we can use polynomial regression to gain insight into neural networks. That's what I was referring to when I talked about the multicollinearity. I'll come back to that if I have time. But secondly, more importantly, again, if we're going to really just be doing polynomial regression, why not do that straight, right? No dealing with all those hyperparameters, which is really a pain. And which there's no good way to decide what's a good set of hyperparameters. You can try a bunch. No convergence issues. No broken clock syndrome. No local non-global minima. No panacea. What are the drawbacks of using polynomial regression? Large memory requirement. And if you've got a lot of variables and you use a high degree polynomial, you're really talking about serious large size matrices. We seldom use more than degree 3. In fact, usually we just use degree 2. But even with degree 2, if you've got 50 variables, you're already talking about a lot of terms in the polynomial. I don't know if you know the big memory package in R. It's really good. You know, R does have problems with memory usage. Before a few years ago, R had really terrible problems with memory usage. And that's why big memory was developed. And the reason, what it does is it takes your R matrix and it does operator overloading, if you know what that is, and basically redirects all your references to that matrix to a C matrix, and now there's no limitation on memory. I don't know how many people here know this, but I just throw in another piece of trivia. Does everybody here know that when we say R is a functional language, we really mean it? Plus, 1 plus 1, that's a function call. There's a function named plus, and we're doing the call plus of 1 comma 1. And left bracket, you know, x sub 5, left bracket is also a function. And so what you can do is you can replace that function with a C function. And that's what big memory does. And you can even have your data on disk instead of RAM. So that's one possibility. Runtime is long, but runtime is long for neural networks also. I'm not sure which one is worse, but it's not perfect. Okay, so we've tried this on a lot of data sets. If anybody has interesting data that they've been using neural networks on, we would love to try our package on it. There's some notation here. We use different neural networks packages. KF is Kara's formula, the one I mentioned that Pete wrote. DeepNet is another one that does neural networks in R, which I like a lot. We use some others. And we calculate the accuracy, mean absolute prediction error for regression, and probability of correct classification in the other case. No data cleaning, by the way. Some of these data sets are really terrible. I'll talk about the New York City Taxi Data. I don't know if you've ever seen that. It has a record of all taxi trips in New York over a certain amount of time. It's a huge data set. There is one record in there where, if you believe it, it was a taxi ride to Antarctica. Presumably an outlier, presumably not right. There are others, and so I have to say there's no data cleaning here. We should. It'd be nice to do, but we didn't. As I said, our method always did well. Side comment, in the neural networks area and machine learning in general, they like to have these contests, and they'll have a leaderboard. So I know some of you know about Kaggle, but there's more than that. I mean, they'll be keeping track on a certain data set who has the world's record right now, the best accuracy. And I wanted to make a comment here because I think most people here have a stat background. A lot of that is really p-hacking, okay? If you know that, very sorry, if you know the term, the idea of p-hacking, you know, multiple inference, simultaneous inference, Tukey's method or Chaffee's method, something like that. If you're doing a lot of inferences, even if nothing's going on at all, probably something's going to turn out, you know, of interest just by accident if you do so many of them. These days, that's called p-hacking. And these contests, these machine learning contests, in a sense, are really p-hacking also. Because just think about it. If many people are trying to break the record on the digit recognition data that I'll come back to, by accident, somebody's going to break the record, right? I mean, the record's like close to perfect already. And if they had another digit recognition data set, maybe they wouldn't do so well. So you have to take these with a grain of salt. Okay. So here's some data from the census. This is data that I put together. It's from the year 2000 census. This is salaries, programmer and engineer salaries in Silicon Valley. The accuracy here is the mean absolute prediction error. Not very good because they don't have much data to work with. There's about 20,000 cases, but not many predictors. There's age, there's education, there's gender, there's occupation, and that's about it. Nevertheless, for us, polynomial regression with degree 4, this is one of the rare cases where we use more than 2 or 3, did the best. Kara's formula didn't even come close. Now, I should say, I have to admit, we didn't play with the hyperparameters in Kara's formula. But nevertheless, we did play with the number of layers, but not otherwise. And it just didn't do nearly as well. Then we predicted occupation in the same data set. So now we're using salary as a predictor. And there are 6 occupations. So again, none of these is really high accuracy, but ours had the best record, better than Kara's formula. I don't know if you've ever seen this data set. The Million Song data set is very nice. It goes back like 100 years, literally. And it would be interesting, this is just for fun, to predict the year of the song. And the predictors here are all audio variables. You know, there are frequencies of this and that. And it'd be interesting because actually if you do some visualization of this data set, what you'll see is right around like 1998 or something, all of a sudden there's a big change. I don't know if anybody can guess. I don't want to use up my time asking to see if anybody can guess. But it's because, now you're going to have to guess because I can't remember. It's something called auto-tuning. I think it's called that. So it makes your voice sound better. And so everybody started using that. And so if you actually look at the data, it changes there at that time. So it'd be interesting to try to predict the year. So we're about 7 years off here. And again, polynomial regression, degree 2, did better than Kara's formula, did better than DeepNet. Not a whole lot better, but still better. Not worse. I mean, they're doing as well, let's put it that way, doing as well with all that nuisance stuff. Convergence, hyperparameters. Another UC Irvine data set, the forest cover. You're trying to predict what kind of grasses or whatever are on the hill there. Maybe because there's no trespassing, you can't go over and look. And you have variables like how much shade is there at noon and stuff like that. And so, again, we did better. 80% accuracy, that's not bad. There are 7 classes. And Kara's formula didn't do as well. One of the readers of our archive paper said, oh, well, I got 75% in neural networks. And so at that time, we had not used the multivariate linear regression yet. And then we did that. We got 80%. So again, pretty good. Here's the taxi data. This is minutes, so the accuracy is pretty bad. Again, you throw all that Antarctica stuff in there, it's gonna make accuracy pretty poor. But again, we did pretty well, as well or better than the others. Okay. What about images? Now, I do have to say this is a work in progress. And, I have to be really fair here to neural networks because that's their pride and joy. Remember, neural networks, nobody even paid any attention to them. Oh. Nobody warned me. I've been trying to shout. Nobody paid any attention to neural networks until the image stuff came up. So they are justifiably proud that the neural networks people are justifiably proud that they do so well on image recognition, sometimes. And so, it's a big deal. And so what happened, I told you what happened when our paper came out, the neural networks people were just enormously defensive, and they said, well, these guys didn't do any images. Well, we wrote why we hadn't. And the critics said, well, if these guys, meaning us, if they would just do the MNIST data, the digit recognition, then we would accept what they're doing as significant. So we did the MNIST data, did pretty well, and they still didn't like it. So, you can't choose, you just can't please them. But nevertheless, it's a big issue. So how well do we do on that? Well, first of all, here's the myth. This is called convolutional neural networks. They do well on images, not because of neural networks. It's not the NN that makes them do well, it's the C. What is the C? The C is standard image operations that people in the image world have been doing for many decades. They break an image into tiles, and each tile they do a summary, maybe a mean, maybe a maximum, median, and that's for dimension reduction, okay? And so it's really the C, and what they've done is they've honed this really, really well so that you can take some of the standard image packages in neural networks like AlexNet and ResNet and so on, and they've already been really tailored to a broad category of images. And so you can do pretty well, but it's not because of neural networks. So the point is that we could do C as well. We just haven't done. We've done a little bit, but not much. Nevertheless, without the C, we just did PCA for dimension reduction, and we did 98.7% on the MNIST data, the digit recognition. It's not the world's record, although I made my disclaimer about p-hacking, but pretty good without even trying. So I think it's I think we can say we're holding our own, and then we're going to use the C stuff. All right, switching gears, the nonlinear PCA. So basically, principal component analysis, that's as old as the hills. Some years ago, people began to say, well, you know, we have a lot of nonlinear data now. PCA is implicitly linear. And so people started to invent new methods for dimension reduction and visualization to replace PCA. And one of the big guys in the machine learning area invented this thing called TSNE. It's an acronym I don't remember. He's one of the big guys. And there's another one called UMAP, which is much faster. TSNE is very, very slow. Well, both of them, though, again, you have the same problem as with neural networks. You have all these hyperparameters that you have to choose, and convergence issues, and so on. So we thought, well, you know what? Let's take regular PCA, but what we'll do is we'll apply polynomials to our original data and then feed that into PCA and use that instead of TSNE and so on. So that package we call prVis. Again, it's on GitHub. So here's an example, Swiss roll. This is not our data. This is artificial data that was developed specifically for this purpose, for these visualization techniques to see how well things work. So it's artificial data. It's a mixture of 4 components. So they basically generate 4 bivariate normals, and then so you now have 2-dimensional data. They run that through 3-dimensional transformations, and they have 3D data, and that's the artificial data. Now, what's the goal? Here's the test. Of all these, TSNE and UMAP, there are many others. What they wanted to do was see how are they going to test this visualization? You know, what's good visualization, what's not? So they said, let's see if we can take this data, run it through the visualization tool, and be able to detect the fact that there are 4 components. All right, so we pretend we don't know that, and let's see if the tool can do that. So PCA is a failure. This is why it's called a Swiss swirl. PCA makes it look like this. It looks like there's one component. Basically, you have this one continuous curve. Here's TSNE. Not too bad in a sense, but you look at this and you say, well, wait a minute. How many components are here? Could be 1, 2, 3, 4, 5. You know, it's not so clear. And so remember, the goal of this particular test is to see if our tool, our visualization tool, can detect that there are 4 components. So it didn't work too well here. So what about ours? Well, of course, this is our killer application. So this is ours, and I would say that, you know, it's fairly clear there that you have 4 components. And so it's working. And of course, we can check. Now I can unpretend, and I can color code the components and see if they came out to what looked like 4 here. And sure enough, it does. Okay. So we're pretty happy with that. Now, of course, all these, you know, you try this on various data sets. It's not as dramatic as this. But we would argue that in a lot of cases, it reveals more than TSNE. Okay. How much time do I have left? Oh, really? Wow. Okay. So what I'm going to do is I'm going to go to my backup slides. Oh. 10. Oh, before I do, I have to show our team. Here's Shi-Chung, who wrote most of polyreg as an undergraduate. She's now a grad student at Cornell. Tiffany is one of the ones who's working on prVis. Bogdan is also an author of polyreg. He's a postdoc at Stanford. Mind you, in biology, he's not in stat, he's not in CS. He's got several CRAN packages, by the way. He's a crack R programmer. Here's Matt, who has also worked on polyreg as an undergrad, although he's a grad student now too. Here's Pete, who I mentioned is the one of the authors of polyreg, and he's a postdoc at Stanford also. He's in the stat department, but he's actually a poli-sci guy. I don't know if you know this, but if you happen to be in the neighborhood in Cambridge, Mass. One time and drop by the poli-sci department at Harvard, and you go inside the circular building, and they have a circular whiteboard around the whole building, you'll see a lot of R there. So you're not alone. Here's Robert Tucker, also on prVis. And then Robin Yancey, who's my PhD student, and she did a little bit on polyreg. And Alan Zhao, also on prVis. Okay, so forget the thanks. Here's the backup slides. Test of a good theory. Does it predict new phenomena? Okay, so I don't want to compare myself to Einstein, which I'm about to do, but just, just forget that. So, Einstein came up with the theory of relativity the early 1900s, and that did not make him famous. But then they tested the theory like in the 1930s because the theory predicted that gravity would bend light waves. And so they said the way we're going to test that is we're going to wait for an eclipse of the sun. We'll go to the eclipse, and then we'll look for stars that ought to be hidden. And if the gravity of the sun is bending the light waves, we might see those stars that are supposedly hidden. And they did. Okay, and that's when he really became famous. So the point is, the test of a good theory is whether it can predict. And so, as I mentioned a couple of minutes ago, our theory predicts multicollinearity in neural networks. Why? Because polynomials, if you use a high degree polynomial, you're going to get a lot of multicollinearity. And so remember what I told you. Each layer in the neural network is going to have a higher degree polynomial. So if what we're saying about the equivalence of neural networks in polynomial regression, if that's true, then there should be more and more multicollinearity in the layers in neural networks. And there is. We checked it out, and it's true. In fact, this is the MNIST data again, Keras package. Some of you may know this thing called variance inflation factor. It's a measure of multicollinearity, and the rule of thumb is if it's bigger than 10, then it's not so good. You have problems. And in fact, in the third layer, it's gigantic. And this was not, the number of layers and the number of neurons per layer and so on, we just took from the example of the neural networks people. And sure enough, that's what happens. So not only does it verify our claim, but also it says, you know what, maybe they shouldn't have had this third layer. So even if you like neural networks, then maybe polynomial regression can give you a few hints here and there on configuring your network. Okay. Now I skipped a slide. That one. Thank you. Yeah.
Is there any kind of mapping between polynomial regression and the tuning parameters of a network?
Well,
and could you use that to I'm in a joining hands kind of
yeah.
Could it be used to maybe find an optimal starting point for search?
Well, yeah, the question was maybe neural networks, maybe polynomial regression could somehow help neural networks in a way beyond what I said about multicollinearity, maybe to help you guess the starting point. I don't really see a way to do that because, when you do linear regression and polynomials are still linear, There's a unique minimum, and it's a convex function. So I don't think so, but who knows, maybe. Somebody else? Yeah, back there.
Could you possibly use genetic algorithms to mitigate the data storage problem with PR?
We should talk offline, and maybe you have a way to do that. The data, maybe. I mean, I don't see the connection right away, but we'd certainly love any suggestions. Right. Anybody else? Yes?
So you benchmarked against neural networks, or have you benchmarked against like GBM?
Right. Okay, so the question was, have we also compared to boosting and random forest and so on? The answer is no, and the reason the answer is no is because we want to play up this equivalence idea of polynomial regression in neural networks, okay? And say, well, first of all, neural networks really are polynomial regression, and secondly, if so, why do neural networks? But everybody knows there are lots of cases where random forest does better, or boosting. Leo Breiman, who used to teach here at UCLA, used to be a consultant in Santa Monica. Did you know that? We're almost done. So he once famously said that boosting is the best off-the-shelf classification method. And sure, we ought to make those comparisons, but we're purely focusing on this equivalence idea, and so we haven't. Okay. Anybody else? Oh, yeah.
I'm sure you've gotten this question before, but one of the more recent sort of implementations of artificial neural networks is in games where there's large search space like Go.
Yeah.
And so I'm just curious whether you've attempted that.
No, we haven't attempted Go yet, that's true. I mean, again, the large search space, maybe there's an issue. As I said, we have memory issues. I don't know. In principle, it should work, right? In principle. But, we're a long way off from trying that. Yeah. And no, we never got that question before. Anybody else? Yeah.
What about the data requirements? So is it that this method, PR method, would be able to work with smaller data sets, or it would not really matter? Like, it would, again, require really large data sets.
Right. Well, the neural networks people would say their method only works on really large data sets. And so our data set of 20,000 programmers and engineers, they would say, well, that's why you do better, because it's too small for us. Ours obviously works on any data, but obviously if you have a data set of size 8, then a cubic polynomial is probably overdoing it.
Not 8, I mean, like, say, 1,000, 2,000, 10,000 points.
Yeah.
Because when these networks are applied, they require, like, big data kind of a thing, or, like, really large data sets.
Yeah.
So if we are talking about, say, economics data, we would not have those kind of data
Right.
points in the first place. So would this kind of approach really help mitigate that data requirement problem?
Well, no, other than the memory issue that I mentioned.
Look, I mean, if memory is not a problem,
Yeah.
would this work if we don't have, like whatever requirement is there for the networks?
Okay, I'm not sure I follow your question. Maybe we should talk offline also. Okay. Anybody else?
Maybe one last question.
Yeah, right.
This is the question of scrutability. One of the motivations in the beginning was, it's very hard to sort of see what's going on
Yeah,
inside
right.
a neural network.
Right.
If you run a polynomial regression, you're going to get coefficients. The most
Yeah.
predictive coefficient is an interaction of the third power.
Yeah, yeah, I know.
That's not any more scrutable. So I wonder
No.
whether or not you guys have given some thought about, especially in like a social science context where people really care about theory.
Right.
You get
Right. So I don't know if everybody heard. I mean, we are out of time, but let me answer. Question was back to the interpretability. We do polynomial regression. We get coefficients, but you have a coefficient of power 3. Interaction of degree 3 doesn't mean anything. Yes and no. Mostly no, but for example, if you're doing linguistics and you're doing something like bag of words, and so the word is either there or not, then a third order interaction means that you have a combination of the three words there together in the same document. That's interpretable, okay? But if you're doing the million song data set and you have a three order interaction of three, audio measures, that's nonsense. I mean, it's predictive. It may be predictive, but you can't interpret. No. All right, thank you, everybody.